So let's summarize. In discrete spaces, what is important is the identification of an honest mass function. Right. Let us test the understanding we've built up by looking at simple examples. So here's the first. For what values of constant, say C, is a particular putative mass function, P of k, defined to be the constant, which is yet unspecified, times 2 to the power minus k, defined on the non-negative integers, 0, 1, 2, 3, and so forth ad infinitum. If one specifies a distribution of this form, is there a value for the constant c which will make it a bona fide mass function, an honest mass function? Pause the lecture and see if you can work your way through with it. Now that you're back, in settings like these, positivity is usually simple to verify. And in this case, since 2 to the power minus k is always positive, we know that if a constant is to work at all, then the constant must be positive. Okay. So in such settings, the question is whether things can in fact be normalized. And the issue here is whether the sum of all elements actually converges, whether the series converges. But in this case, it's a very simple series. This is a geometrically declining series. It's an exponentially declining series, and therefore we have a geometric series formula. The sum of reciprocal powers of 2 is manifestly the reciprocal of 1 minus a half. In other words, the entire sum of 2 to the power minus k, k running from 0 to infinity, is exactly 2. So if we sum up all of the pk's, we'll get 2 times c. Normalization mandates that that has to be 1, and therefore c must be equal to 1/2. Now, once you've written this down, you say, well, this looks familiar, and indeed it is. This, in fact, is exactly the geometric distribution we saw in the last slide. This is the geometric distribution with a particular choice for the parameter. The parameter here is 1/2. Here is a second problem, a slight variation on this theme. This time, I'm going to give you a function, p of k, which is defined as some constant times e to the power minus the absolute value of k, and k is allowed to run over all integers, positive and negative. For what value of c would this be a bona fide distribution? Would this be an honest mass function? Again, pause the lecture while you try to work it out. Well, again, positivity is trite here. The exponential function is always positive, and therefore, if it is to work at all, c must be a positive constant. Positivity is usually trite. And so everything hinges upon whether the series converges. Suppose we add up all the elements e to the power minus the absolute value of k, k running over all integers. We find that at k equal to 0, you get a contribution of 1, and then you get a double contribution for each value of k, e to the power minus 1 for k equal to 1 and minus 1, e to the power minus 2 for k equal to plus and minus 2, and so forth. And so the series devolves into another geometric series. And if we sum this geometric series and massage the algebra, out comes a very simple expression. We get that the sum of this series is e plus 1 over e minus 1. E, of course, is the Napier constant, 2.71828, and so forth. And this is what the series converges to. If we sum the values pk, then we'll get e plus 1 over e minus 1 times c, and this must, by normalization, equal 1. And therefore, c is the reciprocal of this ratio, or in other words, c is e minus 1 divided by e plus 1. Yet one more. Now I will take the function I've just given you, c times e to the power minus absolute value of k, and modulate it by multiplying it by a value which is no more than 1 in absolute value, cosine of pi times k. Can this function, defined as k varies over all integers, be a distribution for any choice of the constants, say. Again, pause the lecture and see if you can verify this. Now that you're back, it would be tempting to test normalization by writing down a series. But we should pause for a moment. The easy axiom to check normally is positivity, and we should always do a sanity check. Are things positive? And we immediately find something troubling. Cosine of pi times k, when k is 0, is 1. When k is 1 or minus 1, cosine is minus 1. In fact, when k is an even number, cosine of pi times k is plus 1. And when k is an odd number, cosine of pi times k is minus 1. The cosine alternates in sign between plus 1 and minus 1, which means that p of k, however we choose c, will be alternating in sign between positive and negative values. Positivity is immediately violated. Whatever be the choice of c, there will be some values k for which these values p of k will be negative, and therefore this cannot represent an atomic probability. P of k cannot represent in an honest mass function.